increase the step of the servo motor and reduce the range of the servos. I think I've already said this, right? Yes, I've already mentioned this. One part of the reduction of the step meant that we could divide the step into 2 mini steps. The movement of walking is based on a symmetric movement. So we walk vertically and there is a central axis. And so we can imagine it, we can prepare the step to be a half step and then repeat it. And so we arrived to 10 by 213 positions. We looked at the different genetic algorithms. So let's say if I start with a step that I've created, I still need a population to improve it. So I still need a different father. If we need to be able to learn to base ourselves on a step that we have already taken in order to learn what we need from it and move to the next one. So one step can generate similar individuals. We do mutations on that step to create similar individuals, and then the algorithm starts to work. We did different tests to see how different they had to be, because we didn't know if there had to be a lot of diversification or not, and we found certain parameters that were large enough in order to be able to use the step. A common problem in genetic algorithms is that the population is too similar, it cannot evolve towards better results. If a population is endogamic, let's say a population of people that live in a tribe and never mix, after many generations, they will probably suffer from genetic disorders or illnesses. If we use very similar robots that are very similar amongst them, they probably will not produce a good step. However, if we have a very high random factor, we will not be able to find 2 parents that are good enough so that they can take a step without falling. And so we need somewhere in between, and that needs a lot of testing. The main limitations of such a project is how to move from a theory to practice. Once we have decided everything, we need to see how difficult it is in practice. We realized, for instance, that the mechanic robot had some problems, some leeway. And so this leeway meant that the joints were a bit loose, and so we needed to make sure that we were going to adapt it properly. And also the environment is important. If the floor is a bit rough, such as if it's carpet, the step is not as easy as if it's an easier floor. So we obtain different results depending on the environment, etc. These would be the individuals obtained through the randomness, and you can see that these ones that say 0 here mean they're so bad that they are not able to go beyond a certain amount of sequences before falling. And here it says at what point they fell. So at the beginning there's only 6. In principle there's only 6 out of 20 that were able to take a step. All the others fell very early on. And we can see how, as generations go by, so, we have parents that they have 30 offsprings, then of those, another 30 offsprings. And after 900 tests, we managed to obtain, with our degree of evaluation, assessment is 4.8, we have managed to reach a level at which there is no further improvement. So the best individual was 3.35. That was the best out of the first 20, and we managed to get it to 4.8. The final population, as you can see, all of them take a step, and all of them are in the range of that situation. The individual we would choose will be the best of that generation. So finally, to conclude on the methodology, in order to obtain this genetic algorithm, normally genetic algorithms are famous because they take very long without having to work with a physical mean. Here in only 30 generations, we were able to optimize the step. An improvement by 40% of the step, certain harmony between the progress, the movement forward, and stability of the system. It was good enough so that the robot was able to go forward, maintaining stability, and also it's quite solid because it is very independent from noise in servers and measurements. It increases the speed in 70% from the beginning to the final solution, and if we've done the test in different environments, and it has shown that you can obtain similar results in different environments. So let's have a look now at the video.
Del robot en movimiento.
Let's have a look at the robot moving.
Hay una cuerda porque una.
As you can see, there is a string, because if there is a total fall to the floor, that would prevent it from going, and the robot's calculating every step, the point at which it can maintain the balance. But as you can see, the structure is not very rigid, and that adds difficulties when making measurements. Also, the marble is at least one of the best floors for him to move on, because the carpet for these robots is really bad. So what's the future work that we have to do? Well, there are some projects on this platform. This is a platform that includes a control area, and that is being improved. We think that it would be necessary to include learning stability or balance. Here you can see a video with the current state of this platform, how it works at present.
Se ve a una persona.
You can see here a person that has motor capabilities. That is, the machine is not totally supporting them. But in other examples, we have people that have less capacity to move. You can see they're totally controlled by a structure. He's never controlling the balance. The machine just rehabilitates the motor part of the individual. After a long period in a coma, for instance. Otherwise, a physiotherapist will have to move it manually. This one is a more natural way of rehabilitating the individual so that he moves and he starts receiving the feeling back. And how could we improve the platform? We believe that our model will have to be more flexible, because it would need the strength of the person. Currently, the sensors are not different to gravity when they move, so there should be some kind of contribution from the robot, and another part of contribution from the user, and modified, adjusted in order to have the best balance, so that the person didn't rock too much from one side to the next. We would also need to have a different robotic structure to the one we currently have. We would need to have adapters similar to this structure, where the pressure sensors would be adapted to the person. Not only the sensor of gravity, but also a sensor of the